So I'll be talking today about pricing shared rides. This is joint work. We have collaborators Chiwei, Shen, and Yifan. So traffic congestion is a major problem around the world. In the US, the average person loses about 99 hours to congestion each year. And this is really driven by low vehicle occupancy, which is about 1.5 passengers per vehicle. So it was really to address this problem, among other problems, that a lot of the ride sharing companies were founded. So, the aspiration of really, if we can get more people in fewer vehicles, then this can be the so-called end of traffic. Right, but despite this very bold goal, I think things have been somewhat different in practice. So this chart shows the distribution of ride type of request types from 2019 to 2023. So light blue is solo requests, so people have no intention of sharing whatsoever. Medium blue is shared requests that did end up being shared. And then dark blue is shared requests that did not end up being shared. So they're kind of fake shared rides. Right, and you can see, of course, there's this blank space due to COVID when shared rides shut down. But even before COVID, and certainly sort of coming out after COVID, shared rides have not been doing spectacularly. So one of the challenges that is highlighted in this sort of popular news article is so this article actually talks about basically the early years of starting shared rides and sort of competition between Uber and Lyft for riding share. And one of the sort of challenges that's highlighted, at least from a pricing perspective, right, is that you want low prices to attract riders to the platform and sort of achieve enough demand density to hit economies of scale. But it's not going to be risky. Because basically, if you charge a low price and you don't end up matching your riders, right, then you effectively just offer this cheaper solo ride product. Right, so we're interested in this tension. Of course, pricing is not the only issue that's there for shared rides. There are also matching and routing problems, right? So which riders should we get with, and also like how should the vehicle travel through the pickups and drop-offs. There are also attempts to coalesce riders more in space and time, either by having to walk or wait or take tours. Right, and then from a pricing perspective, there's also been a lot of work on just how to shared rides interact with solo rides and also on cost sharing. So in our work, we were sort of focused on two aspects. So we were interested in sort of historical pricing policies to understand maybe why shared rides have struggled in practice. And then also, we wanted to propose and discuss a sort of two-tier pricing policy that we showed would better coalesce demand. Okay, so I'll talk through our sort of model of shared rides, and then I'll talk about the pricing policies on this model, and then I'll go through some computational results. Okay, so there's going to be a lot of simplifications for this shared rides model. It's basically like the simplest possible version of shared rides that you could think about. Right, so actually, we're only going to look at one origin destination for a lot of this talk. And the reason is that this basically isolates the pricing decisions from matching and routing decisions, right? Because there's actually really no matching or routing decisions in this kind of model. Okay. We're also going to assume that there's sufficient supply to service the demand. And then there's also going to be a vehicle capacity or two, which is more or less like the effective capacity of shared rides anyway. And then also, we're not going to look at interaction with solo rides. So we have been working on this interaction as well. A lot of the insights are kind of similar, but here we'll just focus on no solo rides. Okay, so just a notation. So P is going to be my price for a shared ride normalized to be between 0 and 1. Right, and then lambda is going to be sort of given this price P, what is the probability that a request is going to a rider is going to convert to a request. Right, and we're going to assume uniform willingness to pay, so lambda is just going to be 1 minus P. Right, so when I talk about pricing, I might refer to lambda or I might refer to P, depending on what is more convenient. Theta is going to be this measure of rider patience. So riders are going to linger on our platform according to like exponential clock that elapses at rate theta. Right, and C is going to be the cost that the platform pays the driver to go from the origin to the destination. Right, and since the price is between 0 and 1, the cost is actually going to range from 0 to 2, where the range 1 to 2 actually corresponds to a regime where the platform has to offer shared rides. It's not actually possible for them to profitably offer solo rides. Okay, so we have some simple dynamics here. So riders are going to arrive and make requests at rate lambda, and the platform is going to make two kinds of dispatches. So they'll make a shared dispatch if another rider arrives and requests a ride, and so this happens at rate lambda, right? And they can also make a solo dispatch if the rider that's waiting on the platform, if their patience elapses, and this will happen at rate theta. Right, so this is a very simple shared ride model, and so we'll talk about what various pricing policies look like on this model. So starting with a static pricing model where just the platform just charges a single price for all riders. Right, so the platform is going to maximize this expected profit, which is just your demand rate times the price minus the expected cost per request. Right, where this expected cost per request under this model of shared rides is given by this function that decreases from C to C over 2 as your demand rate increases. Right, and so just what does this, it's kind of illustrative to look at like what this profit function looks like, because it kind of highlights some of the challenges of shared rides, right? So when your costs are low, we actually have a well-behaved cost function, but we have this weird phase transition when costs are high, right? So initially, basically, as you're increasing your demand initially, your profit is decreasing from 0, and this is because basically there's insufficient demand to get enough match rate to sort of have your lower prices like outweigh these high dispatching costs. And then eventually you get to a point where your match rate can increase enough that it can actually offset these lower prices, right? And so your profits will then have this turnaround. And so this phase transition also sort of evolves with the patience theta. Right, so as theta increases, your lambda star is going to decrease, so going from right to left, right? And actually it's going to drop to 0 abruptly, right? So there's this continuity in your optimal lambda, right? And this sort of manifests like the difficulty of a static price for shared rides, right? Because basically it's showing that in these like high cost and impatience regimes, right, it's really difficult for this match rate to really compensate for this lower price, right? And so you have this discontinuity. Right. So in addition to this issue with the optimal static price, there's sort of like an additional issue in practice because the platform is not going to solve this problem exactly. Right. So we sort of modeled a heuristic which is intended to model sort of what platforms do in practice. Right? So this is what we're calling iterative pricing, right? And so practice, right, the platform might start with an initial price, which corresponds to an initial demand rate, right? And then over a sequence of iterates, right, you look at your demand, right, and you offer shared rides on this demand, right? And then you can see what your costs are, what costs are being incurred sort of by your shared rides product, right? You can calculate the average cost per request. And then you can use the average cost per request to just calculate what your new prices and your new demand levels should be, right? And then you can just keep on updating this process, right? And so why this is kind of appealing in addition to its simplicity is, it could adapt to non-stationarities. It also easily generalizes to multiple origin destinations, right? It does converge in this model to one of 3 values. But we also show that it always overprices. So whatever it converges to, its demand rate is sort of artificially too low relative to the optimal demand rate. Right, and sort of how it converges depends on various parameters. So cost, impatience, as well as the starting point of sort of where the platform initializes their prices and demand. Okay, so when costs are low, things are not so interesting, just regardless of your starting point or the rider's impatience, right? Then the lambda always converts to this lambda bar. Right, but when costs are high, things get a little bit more complicated. So now only in this sort of high demand or low impatience setting do you converge to the lambda bar. Right? There's a sort of uninteresting case where if you start at lambda underbar, you just stay there, right? And then in all of the rest of this area, right, your lambda converges to 0. Right? So this corresponds to sort of either high impatience settings, right? Or sort of interestingly, if your starting point lambda 1 is quite low, right? So we call this like a timid entry into the market, right? So if the platform is like really unsure about shared rides and is just like, okay, I'm just gonna make it like a little bit cheaper and see what happens, right? It can actually drive itself out of the marketplace. And this can happen, of course, even if it would be possible for the platform to offer a profitable share ride. Okay, so having highlighted some drawbacks to static pricing, we now turn to an alternative, which we call match-based pricing. And this is similar to actually some products that Uber has tested in some recent years. But the key idea is that the rider should get a discount if the ride does end up being shared. Right? So if the rider arrives when no request is waiting, they're going to be shown two prices. Okay, it's a little shown. All right, but so there's the first price if the ride ends up being solo, and then there's a second price if the ride ends up being shared. Right, and then we're going to assume that the rider converts based on the expected price, which does require that they have some knowledge of the match rate of the platform. Meanwhile, if a rider arrives when there is another compatible request on the platform, they would be shown one price, just the shared price, and then they convert based on this known price. And this has some similarities to the sort of like pop-up products that Uber has tested in recent years. Okay, so the platform would seek to maximize their expected profit again, and somewhat surprisingly, I guess, there is a closed form solution for the optimal prices and conversion rates in the setting, and they actually are continuous in C and theta. So unlike the static pricing case where we had these weird discontinuities, these prices are well behaved, which makes them a bit more appealing as well. Right, so of course, it's obvious that match-based pricing should have higher profit than static pricing, but there are some other benefits as well. So if cost and impatience are high enough, then the first rider is going to see a lower expected price. For any rider who gets matched, their expected price is always going to be lower than the optimal static price. And then on average, whatever price is quoted to riders, regardless of sort of what state they arrive in, again, when cost and impatience are high enough, they're going to see lower price quotes on average. They also just always will see a lower average or make lower payments on average, and the platform will always benefit from lower cost per request and higher match rates. And so the takeaway here is that under these high cost and high impatience settings, which are the most challenging regimes for shared rides, this can really be a win-win for the platform and the riders. Great. So having sort of compared these two pricing policies on a single origin destination setting, we wanted to scale this up to multiple origin destinations. I'm not going to talk about the model for multiple origin destinations in the interest of time because it's kind of lengthy. But we implemented this in Chicago on a data set with hundreds of origin destinations. We implemented our various pricing policies. Okay, so first we wanted to confirm this result that the iterative heuristic would overprice in this multiple origin destination setting, right? And so here's a map that's just showing the prices for static pricing solved using the iterative heuristic, as well as with subgradient ascent. And you can see by just the darker shades on the map on the left-hand side, right, that this iterative heuristic is, charging prices that are too high. We also wanted to compare, again, the match-based pricing and the static pricing. And so these maps are showing the gap in quoted prices and payments for match-based versus static pricing. So this red shaded area is the downtown of Chicago. And you can see that match-based pricing is quoting slightly higher prices in this dense downtown area, but it's quoting lower prices in the sort of sparser outlying areas. And we see this as sort of expanding access to shared rides where they have been most challenging to operate. And then overall, the right-hand plot, everything is blue, so match-based pricing, is inducing lower payments from the buyers sort of everywhere. We also wanted to look at a metric called cost efficiency, which sort of quantifies how effectively shared rides are operating. So this is a metric that ranges between 0 and 0.5, where a cost efficiency of 0 means that effectively the platform is just operating solo rides, no one is getting matched. Right? And then a cost efficiency of 0.5 means that this is the best that shared rides can be doing. Every rider is basically matched with their identical twin. Right? And so these are the cost efficiencies plotted across Chicago, and you can see that under static pricing, right? In these outer areas, the cost efficiency is very low, and the static pricing is basically operating solo rides in these areas, right? But for match-based pricing, the cost efficiency is sort of healthy throughout. Okay, so just to close, so under static pricing, we showed that this iterative pricing heuristic tends to overprice and suppress the demand, but even the optimal static price is sort of challenging for the platform because it exposes them to the risk of not matching with riders, right? And so our proposal is this match-based pricing, which benefits the platform through higher profit and riders through lower quoted prices when in these sort of challenging shared ride regimes. So that's what we have time for questions.
Well, what's the intuition for why iterative pricing also prices?
Yeah, so basically the platform is sort of ignoring the effect of that raising costs will have on the platform is ignoring the fact that the effect of raising prices on the demand. And so when the demand is suppressed, the cost will also explode, right? Because the match rate is going to reduce, right? And so it's sort of over optimistic about its ability to raise prices, and that's why the
in the match, but see the idea is that you offer me a solo price and a share price with a waiting time. The solo does not have a waiting time.
The solo price would also, so, okay, it's probably too far to that, but the solo price, so basically like
In your model.
in a model, right, a dispatch could happen solo or share, and you would, so basically if the patient of the rider lapses, then it's a solo dispatch, and if another rider arrives, then it's shared dispatch.
And what are the differences in the prices? Is there a consumer choice here that I choose solo
No,
or
you're not choosing solo or dispatch, it's really just like whatever your outcome ends up being, right? So you're consenting to possibly being, matched in a shared ride when you book a shared ride, right? And it's just sort of compensating a little bit extra if you actually end up getting
At the risk of pushing in the direction that you said explicitly you didn't want to cover in the talk, shouldn't the platform overprice to account for cannibalization of actual solo rides, or meaning of like non-shared rides?
So I guess the solo rides, the discussion of solo rides, or sorry, the interaction with solo rides that we're considering, it ends up being, so under a certain like utility model, basically these problems are being separable, right? And so what ends up happening is that like if people's like sort of disutility of sharing is really high, then the platform just offers solo rides, and if it's low enough, then it'll just offer shared rides. So this is sort of the initial work that we're doing, and then there's sort of other models where like you would offer both at the same time.
Does that assume homogeneous populations?
Yes.
Is your conclusion that like in every regime, the match-based pricing is better, or are there in those kind of low-cost regimes, is the iterative pricing better or just the same?
Yeah, so, well, match-based pricing is better than iterative pricing, because iterative pricing is just very poor, right? But it's better than, it's only really better for everyone in the high cost and high innovation, right? So these are like I guess like the high cost regime now is sort of like very high labor costs, right? So it seems kind of plausible, right? And then high impatience is like, these are very on-demand products that people don't really want to like, reserve a ride ahead of time. They want the ride now.